There is a tree sap that sealed Victorian water pipes, insulated the first transatlantic telegraph cable, and resisted acid enzymes and electricity better than almost anything else available in the 19th century. It was called Gutta Percha, harvested from a single species of Malaysian rainforest tree. Polyethylene plastic replaced it in most applications by the early 20th century. One use never got replaced. Dentists have used it for root canal fillings for 170 years, and nothing has ever knocked it off that job. Why did everyone else stop using it? Two things explain why a material that once ranked as the second most economically important plant product in the entire British Empire, after natural rubber itself, has vanished so completely from public awareness. Most people alive today have never heard its name. One involves the specific chemistry of what Gutta Percha actually is. A chemistry so close to rubber, and yet so meaningfully different that it created an entirely separate industrial category rather than simply becoming a rubber substitute. The other involves the arrival of a cheaper, more easily manufactured synthetic material in the early 20th century, and the near-total commercial abandonment that followed once that alternative existed at industrial scale. By the end of this video, you will understand exactly what Gutta Percha is, and how a substance used by Malay communities for centuries became the material that made transatlantic communication possible. You will understand what specific chemical properties made it irreplaceable for one particular modern application even after everything else about it was superseded, and why the tree that produces it very nearly went extinct because of how badly Victorian industry wanted it. The place to start is not with the pipes or the cables. It is with the tree itself, and with a harvesting method that turned out to be the seed of both this material's spectacular rise and its eventual near disappearance. Gutta Percha comes from the latex of trees in the genus Pelequium, part of the broader Sapitaceae family, native to the rainforests of the Malay Peninsula, Borneo, Sumatra, and the surrounding archipelago. The name itself comes directly from Malay geta, meaning sap or gum, and percha, the name of the tree. Local communities across this region had used the material for generations before any European encountered it, applying the sun-dried latex to sealing roofs, waterproofing gutters, and crafting handles for machetes and other everyday tools. The earliest known Western reference to it appears in 1656 in a catalogue written by the English gardener and traveler John Tradescant the Younger, describing a curious substance he called pliable mazer wood that could be softened in warm water and worked into any shape. For nearly 2 centuries after that first mention, the material remained a curiosity. Unknown outside a small circle of naturalists, and largely absent from any commercial application in the West, that changed abruptly in the 1840s. In 1843, a Portuguese engineer named José de Almeida described the material formally to the Royal Asiatic Society in London. Shortly afterward, a surgeon working for the East India Company, William Montgomery, sent samples from Singapore to the Royal Society of Arts, where they were put on public display. The reaction was immediate and, by contemporary accounts, close to a genuine craze. Within a remarkably short period, Gutta Percha was being incorporated into snuff boxes, walking sticks, dolls, chess pieces, jewelry, and decorative objects of every description. The company that controlled the primary import channel from Malaya, appropriately named the Gutta Percha Company, found itself at the center of one of the more unusual commodity booms of the Victorian era. Stay with me, because what made this substance genuinely useful, rather than merely a fashionable Victorian novelty, is where the chemistry becomes the actual story. Chemically, Gutta Percha is a stereoisomer of natural rubber, meaning the two substances are built from precisely the same repeating molecular unit, polyisoprene. They share an essentially identical overall chemical formula down to the last atom. The difference between them lies entirely in molecular geometry, the specific three-dimensional arrangement of atoms along the polymer chain, a distinction invisible to the naked eye, but decisive for every practical property that follows from it. Natural rubber has what chemists call a cyst configuration at each repeating unit along its chain, which produces a loosely coiled, highly flexible molecular structure capable of stretching too many times its resting length, and then snapping back. That structure is exactly why rubber behaves elastically, the property everyone immediately associates with it. Gutta Percha has a transconfiguration instead, which produces a straighter, more tightly packed, more crystalline molecular arrangement, The practical result of this single geometric difference, small at the molecular level but enormous in its consequences, is dramatic. Gutta percha does not stretch and rebound the way rubber does. Dropped on a hard floor, it will not bounce at all. But that same transconfiguration gives it genuine thermoplastic behavior. It is rigid and tough at ordinary room temperature, yet becomes soft and completely moldable when heated in hot water. And it returns reliably to its rigid state as it cools, retaining whatever precise shape it was given while warm and workable. This is precisely the behavior profile of a modern thermoplastic, discovered and exploited industrially roughly 70 years before the word thermoplastic was even coined, and decades before synthetic plastics existed in any laboratory anywhere in the world. This thermoplastic behavior, combined with a set of chemical resistance properties that made it genuinely unusual for its era, is what turned gutta percha from a curiosity into critical infrastructure. It resisted degradation from acids and from biological enzymes far better than most other available materials, meaning it did not rot, corrode, or break down when buried underground, submerged in seawater, or exposed to the organic material found in soil and marine environments. It did not conduct electricity, making it an excellent electrical insulator at a moment in history when electrical insulation was becoming one of the most commercially and strategically important material properties in the world. And it was, according to contemporary accounts, more watertight than rubber itself. Here is where those specific properties turned gutta percha into one of the most consequential materials of the 19th century. The Victorian commercial botany literature of 1890 explicitly ranked gutta percha as the second most important vegetable product exported from the British Empire, trailing only India rhubarb itself in overall economic significance. This was not a minor or specialty material. It was applied at genuine industrial scale to water pipes, buckets, basins, door handles, and drawer knobs, precisely because its combination of moldability, water resistance, and chemical durability made it superior to the available alternatives for exactly these domestic and plumbing applications. Boot soles made from gutta percha were among its first major commercial uses, prized for being genuinely waterproof in a way that leather could never fully achieve, but the application that made gutta percha historically indispensable, the one that justified building an entire global supply chain around a single species of rainforest tree, was submarine telegraph cable insulation. When engineers set out to lay the first transatlantic telegraph cable in the 1850s, one of the most ambitious engineering undertakings of the entire 19th century, they needed an insulating material that could be submerged in seawater continuously for years at a time. It had to withstand the enormous hydrostatic pressure present at ocean floor depths across thousands of miles of open Atlantic. It had to resist the biological degradation that seawater, salt, and marine organisms would otherwise inflict relentlessly on any organic material left exposed for that long. And it had to maintain reliable electrical insulation across a signal path stretching between two continents without a single point of failure anywhere along its length. Gutta percha was, at that specific moment, in industrial history, essentially the only material on Earth capable of meeting every one of those extraordinarily demanding requirements simultaneously. No synthetic alternative existed yet to even compete for the job. The message that first connected North America and Europe electrically in something approaching real time traveled through a cable, insulated with the sun-dried sap of a Malaysian rainforest tree. A fact that most people who have heard the general story of the transatlantic cable have never actually connected to the specific material that made the entire undertaking physically possible in the first place. Gutta percha's reach extended well beyond critical infrastructure into everyday Victorian and Edwardian life in ways that are almost comically varied by modern standards, precisely because a genuinely moldable, waterproof, durable material was such a novelty in an era before synthetic plastics existed in any form. It became the standard material for golf balls throughout the second half of the 19th century, known popularly among golfers as gutties, replacing the earlier and considerably more expensive practice of stitching leather balls stuffed tightly with boiled goose feathers. Golfers of the era discovered somewhat by accident during ordinary play that gutta percha balls that had accumulated dents and scuffs from repeated use actually flew farther and more consistently through the air than pristine, perfectly smooth balls fresh from the maker. This observation arrived at purely through trial and error rather than any aerodynamic theory. It directly led to the deliberate, dimpled pattern manufacturers began pressing into new balls. A design feature still used on every golf ball manufactured today, more than a century after gutta percha itself stopped being the material those balls were actually made from. The material also found use as sealing wax on official government documents in multiple countries, prized for the same moldability and durability that made it useful everywhere else, and as a coating for machine belting and various mechanical components requiring flexibility, combined with chemical resistance in industrial settings. And in 1847, in a development that would prove far more consequential than any of its decorative or recreational uses, gutta percha entered dentistry for the first time in the United States as a material for filling teeth. Introduced during the same remarkable decade that saw the material discovered by Western science, exploited industrially at continental scale, and pushed to the edge of ecological collapse almost simultaneously. This dental application would prove, remarkably and against every expectation the rest of its history might suggest, to be the one use of gutta percha that no subsequent material innovation has ever successfully displaced, even after everything else about the material was rendered commercially obsolete. Here is where the story of this material's supply and near extinction becomes an unavoidable part of understanding why it eventually disappeared from almost everywhere else. Unlike natural rubber, which can be harvested repeatedly from the same living tree through careful tapping of the bark without killing it, allowing a single tree to produce latex reliably for decades of continuous cultivation, gutta percha could not be extracted this way at all. The latex inside Palaquium trees does not flow freely from a simple bark tap the way rubber tree latex does when a controlled incision is made. To obtain gutta percha in commercially useful quantities, the entire tree had to be felled outright, and its bark stripped completely away before the sap would flow in sufficient volume to be worth collecting. A fundamentally destructive harvesting method that made every gallon of raw gutta percha the product of one dead, mature tree rather than a renewable annual harvest that could sustain itself indefinitely. The consequences of this destructive extraction method were severe and remarkably rapid once Western commercial demand took hold. Sir William Jackson Hooker first formally described the tree botanically in the Journal of Botany in 1847. At almost exactly the moment Western commercial demand was exploding across multiple industries simultaneously. Between that year and the 1870s, uncontrolled and enthusiastic exploitation of the wild population, entirely without any organized program of replanting or sustainable management, drove the species to the edge of extinction across large portions of its natural range in barely 2 decades of intensive harvesting. This was not a slow, gradual depletion, playing out gently across multiple generations, the way overharvesting sometimes does. It was an extraordinarily fast collapse of a wild biological resource, driven directly by the very commercial success that had made the material internationally famous in the first place. And it stands today as one of the more striking early examples of a Victorian industrial supply chain running headlong into an ecological limit that nobody involved had anticipated, and that no one had any established plan to manage. The extermination of the wild tree population was ultimately avoided, but only through the deliberate establishment of gutta percha plantations. A shift from wild harvest to managed cultivation that mirrored what was simultaneously happening with rubber trees during the same era of British and Dutch colonial agricultural expansion across Southeast Asia. Plantation cultivation stabilized supply going forward, but it came only after the wild resource had already been driven to the brink by a harvesting method that made destruction, rather than sustainable extraction, the price of every unit of raw material obtained. Now here is where conventional industrial history and the specific fate of gutta percha diverge from what its Victorian champions would have expected. Gutta percha's dominance in submarine cable insulation and general industrial application began to erode in the early 20th century with the development of polyethylene and other petroleum-derived synthetic plastics. Polyethylene offered several genuine decisive advantages over gutta percha as an industrial material. It could be synthesized from abundant petroleum feedstock rather than harvested from a slow-growing tropical tree that took years to mature, and even under plantation cultivation, remained geographically limited to a specific climate zone. It could be manufactured at essentially unlimited industrial scale in a chemical plant located anywhere in the world. Rather than depending on shipping raw latex from Southeast Asian plantations to processing facilities elsewhere, and critically, its material properties, including electrical insulation, performance, and chemical resistance, could be engineered and adjusted through the manufacturing process itself, rather than being fixed by whatever a particular tree species happened to naturally produce. By the early decades of the 20th century, polyethylene and related synthetic plastics had displaced gutta percha from submarine cable insulation, from water pipes, from buckets and basins, and from the great majority of the domestic and industrial applications that had defined its Victorian commercial success. This was not the result of any deliberate suppression or industry conspiracy against a natural material. It was the straightforward outcome of a synthetic alternative offering equal or superior performance at a fraction of the cost, and with none of the supply chain vulnerability inherent in depending on a single tropical tree species. The economics were simply overwhelming, and industry adopted the cheaper, more scalable, more consistent material as quickly as manufacturing capacity allowed. One application, however, never made that transition, and understanding why reveals something genuinely interesting about the limits of substitution, even in an era of otherwise total synthetic replacement. Gutta percha entered endodontic dentistry, the specialty concerned with root canal treatment, in 1847, and it remains the standard material for root canal filling to this day. A continuous clinical use now spanning roughly 170 years. In a root canal procedure, after the infected or damaged pulp tissue inside a tooth's root canal system has been removed and the canal has been cleaned and shaped, the resulting empty space must be filled and sealed to prevent bacterial recontamination and to provide structural support. Gutta percha remains the material of choice for this specific application because its exact combination of properties, developed by a rainforest tree rather than by any chemist working toward a dental specification, turns out to be almost perfectly suited to the requirements of the job. It is biocompatible, meaning it does not provoke a significant inflammatory or toxic reaction. From the surrounding living tissue that borders the root canal, it is thermoplastic in exactly the way needed for the procedure, softening under controlled heat so it can be compacted fully into the irregular, branching internal geometry of a real tooth's root canal system, and then hardening again as it cools to form a stable long-term seal. It resists degradation from the fluids and biological conditions present in the human mouth and jaw over years and decades. And unlike many alternative filling materials that have been proposed and tested over the intervening century and a half, it can be removed relatively cleanly from the canal if a root canal treatment ever needs to be redone. A property called retreatability that has proven surprisingly difficult for synthetic alternatives to match. Multiple newer materials have been developed and tested against gutta percha in dental research over the decades since its introduction, including various synthetic resins and other polymer formulations engineered specifically to compete with it. None has managed to displace it as the standard of care. The material a Victorian surgeon first tried in a tooth in 1847, harvested from the same species of Malaysian tree that once insulated transatlantic cables and sealed drinking water pipes, remains, in this one specific application, the thing nothing else has ever quite matched. This is the part of the gutta percha story that is genuinely remarkable rather than merely nostalgic. It is not that a forgotten natural material was secretly better than everything that replaced it across the board. In almost every application where it was used, a synthetic alternative eventually did displace it, for entirely legitimate reasons of cost, scalability, and consistency that a naturally harvested tropical latex simply could not match once industrial chemistry matured. What is remarkable is the one place where none of those advantages proved sufficient. A tree that Malay communities had been using to seal roofs and craft tool handles for generations before any European ever heard its name, produced a chemical structure so specifically suited to one narrow, exacting medical application that a century and a half of subsequent materials science, backed by enormous pharmaceutical and dental industry research budgets, has never quite managed to improve on it enough to make the switch worthwhile. The tree still grows in the rainforests of Malaysia and Indonesia, now under plantation cultivation rather than the destructive wild harvesting that once nearly eliminated it. The sap it produces is boiled, refined, and shipped in a form barely different from what dental supply companies were producing well over a century ago. It no longer seals a single water pipe or insulates a single mile of undersea cable anywhere in the world. All of that having long since been handed over to synthetic plastic manufactured in facilities that owe nothing to any tropical forest. But in the dentist's chair, in the specific narrow procedure of a root canal, the sap of a tree first described scientifically in 1847 is still after 170 years. And against every synthetic competitor chemistry has produced, doing exactly the job it has always done. If you found this genuinely useful, watch the next video and do not forget to subscribe. See you in the next one.